My warm welcome to the judging panel of the DoBASS UAV design competition of the Aeronautical Society of India. I am Savesh Bhaskar from Team Do Vortex, and this is a stage one 10-minute video presentation. We'll be looking at our solutions to different parts of the problem statement, starting from the VTOL drone, and then the part selection, and then the docking system, and then finally the battery swapping mechanism. But before that, we'll head on to the literature survey and get to the literature survey papers which stood out to us and made us design the solutions to the given problem statement. Starting with the literature survey, you'll get started with modifying the existing fixed wing UAV to VTOL. In this, upon researching on many papers, the two papers which stood out to us and helped us design our solution, where the case study on converting a fixed wing surveillance UAV to VTOL for urban operations, and then the design and conversion of fixed wing UAVs to VTOL drones, and then the same for drone docking mechanism. The papers which helped us design where precision landing of UAV and moving platform for outdoor applications, and a decade of UAV docking stations, brief overview of mobile and fixed landing platforms. And then again, for a battery swapping mechanism, we use the paper systems and the methods for UAV battery exchange from Google Patents. Now let's start discussing the solutions for the given problem statement, and let's begin with the VTOL drone part itself, where where in the proposed problem statement we were given a mini Talon UAV. We are converting into a VTOL drone. Now the this is our model, the proposed fixed wing VTOL model, where we went to a quadcopter kind of a quadcopter kind of approach, which so that it ensures stability for vertical lift, and also a quadcopter model can easily be controlled by anyone controlling it. Now we also found out the center of gravity and the inertia measurements, and these are the COG and inertia measurements found out. Then for the propeller position, we found out that it would be optimal, from the literature survey, we found out that it would be optimal to place the propellers at a distance of 250 millimeter from given on the given central axis, and at a distance of 300 millimeter from the other perpendicular central axis. Flight time of the VTOL at 100% thrust, it would take around 10.4 minutes, and for 80% thrust, it would take around 13 minutes. Now, this is a graph which shows the thrust versus RPM of the proposed VTOL model. And then let's get on to the next part of the problem statement. Now, coming to the path selection part of the problem statement, the selection of propeller motor and suitable electronic speed controller for the VTOL designed. We'll look into the proposed propeller motor and EAC specifications right now. Now, the propeller motor that we propose to use in this model is the 920 kilowatt brushless DC motor for DJI. The selection of the electronic speed control, it's based on the motor specification of the electronic speed control of 30 amps. The specifications obviously is the motor kilowatt rating would be 920 kilowatts. The thrust it would produce would be around 0.5 kg. LiPo battery, it can be a 3S to 4S range. The electronic speed control would be 30 amps. The shaft diameter of the motor would be 6 mm, and the propeller size is 8 to 10 inch. Selecting this motor would ensure that the thrust ratio would be 2:1, as each propeller would be producing a thrust around 0.5 kg, and for the proposed model the weight would be around 1 kg. So it makes a thrust ratio of 2:1. And now moving on, we come to the third part of the problem statement, which is the docking system, which involves the docking of the drone in the mid-air and the aerostat, where this is a proposed model to docking station. Talking about the docking mechanism, we can start with the docking assistance mechanism. We can see the fiducial marker would be simply a QR code. And using this QR code, the readings from the monocular camera, the drone can perceive on where it should land, and the landing, the actuators and the screw nut mechanism, which we are going to use, starts working. Where the two yellow rods, which you can see, would now move the drone to one corner of the docking base that we have in the aerostat. Now, the drones would have special fixtures, which make sure that the drones, get attached to these rods, and then so that these rods can successfully move these move the drone, the UAV, to a corner where where the battery swapping mechanism actually happens. Now, moving on to the first battery swapping mechanism, it would be better if we start with the battery replacement before the battery removal. Now, this is the initial stage in which the whole system looks like. This battery pack has components inbuilt for the locking of the battery. Now, we can see that there are two wedges present in this system, and which are connected by a single rod. Where between those two wedges, there is also spring constraint between these wedges, and we can also observe that we have an inner the inner wedge on both the sides has a small opening through which a pin moves along it when the battery replacer is activated. Now, when the pin moves along, when the pin which is present moves along the inner wedge, this moves the whole system in this moves the whole system in such a way that the spring gets the inner spring that's the inner wedge moves inside, moving the outer wedge also inside, making the spring compressed, and there's also which makes the battery remover able to remove the battery. Now the magnets present here support the holding of the battery, support in holding the whole battery pack. And now for the this using this mechanism, battery is removed. Now for the battery replacement process, a simple push will move the wedge inward, and the battery will be pushed into the drone. On reaching the proper position, the wedge will lock the battery pack itself. So basically, this is how this first mechanism works. Now, moving on to the next one. Now, moving on to the second battery swapping mechanism, we can again split this into two different parts. First, beginning would be the battery removal mechanism, where you can observing the initial stage, you can find that there are two pin-like structures present, and then clip-like structure present, and in between them there is an electromagnet, and these two clips are suspended by a spring. Now, at the initial stage, the permanent magnet has a battery cover on its outside, right? Now, when the spring on the clip on the right, is actuated in such a way that it removes the, it lose removes the lock of the battery cover present on the battery. Now, the electromagnet would get actuated, like it would get actuated and it would get turned on, and then the battery cover would get, attracted to the electromagnet, and it would be removed from the battery. Now, this battery cover, after completion of battery cover removal stage, now basically we've been mechanical engineers. We got we got inspired for this mechanism from our capstan lathe, where we use the where upon the completion of the first mechanism, the second tool arrives. The second tool here being the gripper. The gripper's mechanism is simple and simple, which it just grabs the battery from its position on the UAV, and then it that completes its function. Then upon this marks the end of the battery removal process. Now, for the battery replacement, the batteries are arranged in such a way that in a characteristic manner, when the batteries are the battery is now replaced by battery is now replaced from this cartridge on the UAV. And then now the battery cover, which was taken in the first stage, is now brought back by the capstan lathe mechanism, where the cover is placed upon the battery's position. Now, the like clip present in the left side now pushes the cover onto the battery, which locks the battery cover at its place, completing this battery replacement process. So that's it. Thank you from Team Blue Vortex. Thank you.